Okay, so this is some help for 3.6, working with momentum. We're going to look at question number 7 first. And question number 7 says, calculate the momentum of a 2,000 kilogram elephant charging a hunter at a speed of 7.5 meters per second. Well, this is actually really straightforward because we know momentum is the mass times the velocity of an object. And so the momentum of an elephant, that's 2,000 kilograms, times a speed of 7.5 meters per second. Moving pretty quick for an elephant. We multiply those together. 7.5 times 2,000 should come out to 15,000. So this is, momentum is 15,000 kilograms meters per second. So there's our first answer. The next question that it goes with is compare the elephant's momentum with the momentum of a tranquilizer dart fired at a much higher speed. So we're going to shoot at 600 meters a second, but it's a very small dart. Okay, big velocity, small mass. We should still get some momentum out of this. The idea is that, is the momentum of the dart going to stop the elephant, or does it still have to have the tranquilizer effect? If you hit something hard enough, it's going to stop. Just naturally, its own momentum will be overcome. But I don't know if we're going to have enough. So we look at the momentum of the dart. We have a mass of 0.04 kilograms times the speed of 600. And if we take that 0.04 times 600, we only get 24 kilograms meters per second. So the key idea, I guess, that we want to present here is that, just hitting the elephant with the dart is not going to stop it. That's obvious. It should be obvious, and clearly the numbers tell us that we don't have enough momentum. So the tranquilizer not only has to hit the elephant, but then it also has to transfer the drugs into the elephant's system to be able to tranquilize it. That being said, this is the funny part. What's the momentum of the 90 kilogram hunter at 7.4 meters per second after missing the elephant? So he misses the elephant, turns around, takes off to run. Well, let's keep in mind, if the elephant's running 7.5 and the hunter's running 7.4, if the elephant doesn't run out of energy, it is going to catch that hunter and run it down. So that's not a good plan for the hunter. But here we'd have a momentum again of the 90 times the speed of 7.4. And yeah, we throw that in the calculator. It's going to come out roughly 666. Let's go ahead. 90 times 7.4 is our 666 kilograms meters per second. All right. Let's go ahead and look at one more problem before we're done for the day. And we need to look at, I think, question number 12. Yeah. We don't often talk about it, but I'll get that to leave me alone. All right. One hazard of space travel is debris left by previous missions. So you go up there and you leave something behind in orbit, and when you hit that, if you hit scraps that are just laying around, that can be detrimental to you, and it could actually cause some pretty serious damage. There are some large enough to be detected by radar, so you can know that they're there and you can avoid them, drive around them. But there are a lot of very small objects, some even as small as a fleck of paint. So this is a chip of paint off of a spacecraft. I'm telling you right now, if I run into a chip of paint, I don't think it's going to hurt. I might not even notice that it's there. But we have to remember that spaceships are going to be moving pretty dang fast, and a collision with a paint chip is going to happen very rapidly. We're going to hit it, it's going to bounce off, and what's going to happen to our spacecraft or our windshield? And so in this problem, we're going to go ahead and look at, hold on just a second. Okay, sorry. So on question 12, so we want to know what amount of force is going to be experienced by that windshield. So let's take a look at what we're given. If we start looking at what we're given in question number 12, it says that we have a force being exerted by a 0.1 milligram chip. Now, this is really important. A milligram, the milli means E negative 3. But we're supposed to do masses in kilogram, which is E positive 3. So this is E negative 6 for kilograms. So this conversion is a little tricky, and so that's why I wanted to help you with it. The mass that we're going to use is 0.1 E negative 6 kilograms. Okay, so we have to get it to kilograms. That's a 6-digit move. This thing is tiny. Okay, in terms of mass, it does not have a lot of mass. It's literally just a chip of paint, and we're flying at a relative speed of 4 times 10 to the third. That would be 4,000 meters per second. So our velocity is 4,000 meters per second. That's its speed relative to the spaceship. So between the two of them, they're moving at a difference of that speed. Given that the collision, the time lasts 6 times 10 to the 6 E negative 8 seconds. The question is, how much force is applied? So we have to understand a couple of things. That we're going to just assume that the paint hits the windshield and then is deflected at a speed of 0. So we're going to let all of its velocity dissipate. Maybe it sticks to the plane, maybe it brakes when it hits the plane, and so those kinds of things. We're going to look at a delta V as being all of our velocity. So that's kind of a key idea to make this work. So in the world of momentum, we know that F delta T equals M delta V. And so our F would equal the mass 0.1 E negative 6 times the change in velocity of 4,000 divided by the time. I'm just going to divide that time over of 6 E negative 8. When we go ahead and make this calculation, we find out that the force applied by the vehicle, or by the paint on the windshield, is actually really big. If you take that 0.1 E negative 6 times 4,000 divided by 6 E negative 8, we end up with 6,666 or 667, so 6,670, there we go, newtons. That's a lot of force for a small flick of, a small chip of paint. So, you know, as much as, it's just a piece of paint, the more debris we get in space, the more complicated it's going to be to get out of our own atmosphere and into space. So it's really important that we're mindful of what's there and how do we clear the debris. You know, all that stuff will burn up on re-entry. We just need to make sure that it does come back down to the Earth, that it's not moving so fast, that it's in its own orbit. I mean, that fleck of paint, without air resistance to slow it down, can stay in orbit indefinitely. So we need to do things to make sure that we clear the field, if you will. Hopefully that'll help you and get you through the homework. We'll see you in class.